All right, so last time we had gotten a little bit involved in this idea of rational numbers. Just to kind of bring you back to speed where we were talking about the fact that rational numbers are numbers that can be written as a fraction, where the numerator and the denominator are integers. So there are some things that get excluded, right, like pi. We talked about that one as a common one. And if it has something where it's written as a decimal on top or something like that, that's not necessarily bad. It's just not in sort of a simplified form. It can be changed in some way that we can write it as a ratio of integers instead. So we were on example 7. All right, so we have a student, and one of these fun things you're going to get to do, definitely the best part of teaching, is grading students' work. It's fun. But in all seriousness, that's what gives everybody feedback so that they know what they don't understand and can get help on what they don't understand. Because if you didn't think you were doing it right, you probably wouldn't have done it that way to start with. You probably thought there was some legitimacy as what you were doing. So this student has done some work. We've got m plus n over p plus n. That's the original problem. And then they simplified it to m over p. And your book likes to ask this question that says, what would you do to help the student? So first of all, whenever it asks a question like that, it's expecting you to give some sort of a verbal answer. So you're going to be writing me down something, several sentences probably. It may have numbers in it. You may have some examples with things in it. That's fine. But you're definitely going to be giving some verbal language, right? So let's first just talk about what in the world the student did and why they might have done it before we actually formulate an answer to them. Because that's what you would do when you were looking at this. I hope you wouldn't just say, no, that's wrong, because that's really not very helpful for the student, because they don't really understand why it's wrong if you do that. So what in the world did the student first do? They might have done that. You're right. Sorry, Shelby. They might have subtracted in off the top and subtracted in off the bottom. What else might they have done? Yeah, they might have done something where they just sort of like drew this line through it. A lot of times you'll see students do something like this. Just draw a line through it and cancel it out that way. Now, in essence, when they did that, they really did sort of subtract the top and the bottom, even if that's not what they were thinking of. So that's what they did. Why might they have done that? I mean, there is an occasion where we do this sort of thing where we draw a line through something and we just eliminate it. But it's not this one. When would we have done that and it actually be appropriate? Yeah, when it's multiplication, right? And in fact, multiplication and simplification of multiplication with fractions is a lot easier than addition and subtraction with fractions. So they're probably thinking of something that's actually, something they've seen before. They just haven't seen it in this context, and they're trying to, sort of bring in something that doesn't really quite fit here. Does that make sense so far? So I'm a strong proponent of the fact that I think that when a student does something, you should try to tell them that they're right, sort of, right? There's something right in their thinking. I mean, they didn't just sort of just come up with this out of nowhere. I mean, not usually. So we might want to tell them something like, that does work, but it doesn't work with addition. It works when you do multiplication, which is kind of what you guys were saying. Thank you. So that's the first thing I would do. You start out by saying, that is actually something that we're allowed to do with multiplication. So let's do something like that. Okay, so the first thing that we've done, and it doesn't necessarily have to be first, I kind of like to put it first, is to validate that they didn't totally butcher the thing. Now, they didn't get the right answer either, so we can't just gloss over that fact either. Now we're going to have to tell them that you can't do that with addition, and if we stop right there, that's still not very helpful. You can do that with multiplication, but you can't with addition because, well, why not? I mean, why can I do it with one and not the other? That sort of seems arbitrary unless we follow that up with a why. So think for me, why could we or how could we show them that this doesn't work with addition? What could we do? Put some numbers in there. I think that's a very helpful thing to do, is to give some examples, especially like on this one where it is starting out with letters everywhere. And it looks a little bit, abstract. So we would want to say this won't work with addition. And you could also even say a subtraction too, but it's addition in this particular problem. And then you can tell them something like this. For example, now you have to be careful and actually make up an example that doesn't work. Okay, be careful on that, because sometimes you'll inadvertently make up something and they're like, see, I told you. And you're like, well, okay, it worked on that one, but not on all of them. So usually when you're trying to show something doesn't work, you want to stay away from numbers like zeros and ones. Usually you're okay if you steer clear of those particular numbers. So let's create an example where we have two numbers added on top, two numbers added on bottom, and the second of each of those numbers is the same. So what would you like to add on top? Make them small. Don't go crazy on me. 2 and 3. All right, so we have 2 plus 3. And since you listed 3 second, Carly will list 3 also on the other one, right? Because they are supposed to match. That is actually part of the way the problem's originally set up. So what would you like to let the third number be, or the fourth number, depending on how you're looking at this? The missing 5. Okay. All right, so if we were to actually simplify this, not reduce, we actually have numbers so we can actually combine things. What would they combine to give us? 5 over 8. Perfect. All right, so now let's take this same idea and let's do what the student did. That is, let's eliminate the 3's on the end, and then we would get what? 2 over 5. We can argue that these two values are not the same in several ways, so this is a good chance for us to remind ourselves from last time. What are some of the ways that we can show that these are not the same? There's lots of them. You could cross multiply. Excellent. What else could you? You could draw a picture, and as long as you're careful with the picture, these two especially will be very clear that one of them is much larger than the other one. What else could you do? Common denominator would be a great idea. You could either do it, well, in this case, the least common denominator would be the common denominator as well. Yeah. And eventually, if you were working with decimals as well, you could do something with decimals, right? I mean, we're not doing that in this section, but there's lots of ways that we can show that these two are not the same. And if these two are not the same, then the ability to sort of just eliminate the 3 like they did right here, it's not something that generally would work. So we can argue, see, it doesn't work in that case, so it's not going to work in general. Again, that doesn't mean there's not some random somewhere case that it would work for, but that's not generally the point of what you're trying to do, is you're trying to find something that always does work. Okay, does this make sense to everyone? All right, the next one is a little bit interesting. It's not a, you're not going to have a super similar example like this in your homework, but I want you to see an example where they're using rational numbers in a little bit different way. That's what I want you to see. So we're going to take a set of numbers equivalent to 1/3. So let's just start with that sentence and make a list of numbers equivalent to 1/3. We did that last time. So what's another number that's equivalent to 1 over 3? 2/6. Can somebody give me something with some negatives involved? Look. Yeah, you could put a negative on the top and on the bottom, -1 over -3. Yeah. Let's do maybe also then the -2 over -6. Is that okay with you guys? All those are equivalent to the 1/3. Okay, so it says we're going to take the set of numbers equivalent to 1/3, and we're going to graph them as points on the xy axis so that the numerator, these numbers on top, become x, and the denominator, these numbers on bottom, become y. Okay, so what they're telling you then is that this first one right here becomes the ordered pair 1, 3. This becomes the ordered pair 2, 6. This one becomes the ordered pair -1, -3. This one becomes the ordered pair -2, -6. Are you okay with that language so far? It's a little bit strange what we're doing, but we're good so far. Okay, great. Now it says we're going to graph these. And we want to know what type of graph we get. That is, what does the picture look like once we plot these points and sort of connect them? So we're going to plot these on an XY plane. I don't know if I've got, look at that. I do have one set up in here. Okay, I'm going to use 2 of these to actually be one value just so I can spread it out a little bit. More or less. So when I'm doing the 0.13, I'm going to come over here to, you know what, I won't, because I think it's going to make things more confusing. Okay, so here's 1, 3. You go right 1 and up 3, right here. And then I have the value 2, 6, so that go right 2 and up 6. I have the point right here. I have the point -1, so I go left 1 and -3, so it's down 3. And then I have the point -2, so I go left 2 and -6, and I go down 6. Those are my 4 points currently. What are they going to look like if I connect them? They're going to look like a line. So let me start with connecting them, and then we're going to talk a little bit about that line because it's almost a line. There's something about this that's not quite right. 0, 0. What's wrong with 0, 0, Rachel?
It's not equivalent to 1/3.
Yeah, this point in the middle, and it definitely is crossing here at 0, 0. It's not equivalent to 1/3. It's the only one that's not, so everything else is fine. But that particular point, you can't do a ratio and get 1/3. So when it asks us what kind of graph we get, we're going to get a line. You might even recognize a little bit more about the line. So it's a line through the origin. What can you tell me about the slope?
1/3.
Close. 3. With slope 3. Slope is always rise over run. So this rises up 3 and it runs over 1. So it's a line through the origin with the slope, so the slope 3. But the origin, I'll write 0, 0, but you could actually write the word origin, isn't included. And you might even jot yourself down the reason why, which is exactly what we said. Because it isn't a ratio of, what do we have? 1, 3. Does not have that ratio of 1 to 3. Okay. It's kind of an interesting example. All right, any questions on that one? No? All right, so this was the group work and homework for that, and we'll get to this before we end class today.